Here's a wild idea. What if I told you that just about anything complex, the sound of an orchestra, a photo on your phone, even the crazy up and down of the stock market, could be broken down into a bunch of simple, predictable waves? Well, that's exactly what Fourier analysis does. It's like having a pair of mathematical glasses that lets you see the simple, beautiful patterns hidden inside all that complexity. Okay, so to really wrap our heads around this, here's our game plan. First, we're going to start with a pretty weird but powerful concept, geometry for functions. Then, we'll find our perfect building blocks and figure out how to write the function recipe. After that, we got to ask the big question, does the recipe work? And finally, we'll see how this all connects from theory to reality. So, let's dive in. All right, let's kick things off with our first section, geometry for functions. Now, I know that sounds a little strange, right? But trust me, this is the foundational idea that makes everything else click. We're about to take concepts you know from geometry class and apply them where you'd least expect it, to functions. I mean, just stop and think about that for a second. How would you even go about measuring the length of a function? Or, and this is even weirder, what could it possibly mean to find the angle between two completely different functions, say a sine wave and a parabola? It sounds like we're mixing up categories, doesn't it? Well, that's where the genius comes in. To solve this puzzle, mathematicians came up with this incredible framework called an inner product space. This is the secret sauce. It's a set of rules that lets us treat functions as if they were vectors. And just like that, those fuzzy ideas of length, distance, and angle suddenly get a real, solid mathematical meaning in this new space. So, check this out. On the left, you've got the world we all understand, vectors, arrows with a clear length and an angle between them, simple. On the right, you've got the abstract world of functions. An inner product space is basically the bridge that connects these two worlds. It lets us use the simple, intuitive rules from the left to analyze the complicated stuff on the right. It's how we start building a geometry for functions. Okay, so we've built this new space where our functions can live. But what good is a space if you can't navigate it? We need some kind of coordinate system, right? We need the function world equivalent of our good old x, y, and z axes. Think about it. In regular 3D space, our axes are perpendicular. They hit each other at a perfect 90-degree angle, which means they're totally independent. Well, we need the exact same thing for our functions. We need a set of functions that are perfectly independent, and we have a special word for that, orthogonal. And this right here is the key analogy. Just like the x, y, and z axes are independent, you can move along the x-axis all day and your y and z position won't change a bit. Orthogonal functions like sines and cosines have that same kind of independence. They form a perfect set of axes or a basis for our brand new function space. So we've got our space, we've got our axes. Now we get to the really cool part. How do we actually use them? How can we take any gnarly, complicated function you can think of and describe it using our simple, clean sine and cosine axes? Well, this is where we learn to write the recipe. And this recipe has a name. It's called a Fourier series. You can think of it as the literal recipe that tells you exactly how much of each simple wave, each ingredient, you need to mix together to build your original complex function back up. It's like knowing you need 2 cups of sine wave, 1 cup of cosine wave, and so on. And here is how it works. First, you just pick the function you want to build. Now, step 2, this is where it all clicks. You use that inner product we talked about to measure how much your function aligns with each one of your basic wave axes. Those measurements give you your coefficients, the exact amounts for your recipe. And finally, you just add all those pieces together. That's your series. Now, this all sounds a little too good to be true, doesn't it? And there's a catch, a pretty big one. For most of the functions we care about, our recipe needs an infinite number of ingredients. And anytime the word infinity pops up in math, you've got to be really careful. How do we know this whole thing doesn't just fall apart? No, seriously, what could go wrong? When you add up an infinite number of things, you'd think the sum would just shoot off to infinity. Or maybe it just kind of wiggles around forever and never actually lands on the function you were trying to build in the first place. There's a lot that could go wrong here. This is where mathematicians roll up their sleeves and bring in the heavy machinery. It's something called convergence theorems. You can think of these theorems as the official quality control for our recipe. They give us a mathematical guarantee that for most functions we care about, the sum doesn't explode. They prove that as you keep adding more and more waves, you get closer and closer and closer to your target until you basically nail it, even for weird functions with sharp corners or gaps. So after that whole journey through abstract spaces and infinite sums and all that theoretical stuff, we finally get to the payoff. We've built this amazing, powerful toolkit. But why? Who cares? Why does this matter in the real world? Well, the answer is it's kind of everywhere. Fourier analysis is the engine running behind the scenes of our digital world. It's at the heart of how we process audio and image files. It's how JPEG compression works. It's used to analyze vibrations and bridges to make sure they're safe. And it's absolutely essential in the bizarre, wave-based world of quantum mechanics.
And hey, you don't even have to take my word for it. This right here is the table of contents from the actual chapter that inspired this. Just look at the progression. It starts with inner product spaces, orthogonal families, all that abstract theory we just covered. And where does it end up? Applications and quantum mechanical formalism. This shows you the direct path from a pure mathematical idea to a tool that literally changes the world.
So let's leave it with this final thought. What Fourier analysis really teaches us is that things that look messy and chaotic on the surface can be built from an incredibly simple and elegant foundation. It gives us a brand new way to look at the world, not as a jumble of data, but as a huge, beautiful symphony of simple waves. And it makes you wonder, if something this complex can be built from something so simple, what else is hiding right there in plain sight?